Our next talk is going to be from Garikoitz Lerma-Usabiaga from, I apologize if I didn't get your name correctly. You can correct me when you begin your presentation. So I'm sorry about that. But his presentation is titled The Gradient of Population Receptive Field Stimulus Dependence in Ventral Visual Cortex. So you can take it away.
Thank you. So Gary is enough. I was lucky enough that my name works well in English.
Yeah, all right, Gary, it's gonna take it away.
Yeah. Okay, so good morning, or wherever you are. So today I'm going to show one result that we've got, and this result is based on a work in my previous group, which is Rosemary Lee and Michal Ben Shahar and Brian Wandel. They published it in 2017, and it is going to be a very simple presentation, and I'm very interested in hearing feedback and questions, because we are now thinking on how to explain these results. So basically, we are going to show the stimulus dependence in the ventral visual cortex. So population receptive field stimulus dependence in the ventral visual cortex. So my group, well, now it is known from many years that there is a region in ventral occipito-temporal cortex that is more responsive to words, right? That
Gary, I just want to make sure.
Yes?
I just want to make sure. Are you supposed to be sharing your screen at the moment?
I'm not. Oh.
Oh no, you're not
sorry.
sharing your screen. Yeah, I just want to make sure.
Oh shit! Sorry.
No problem.
No, I was in full screen. Is it working now?
Oh yes, it's working now. You're good.
Okay. Well, the first slide was just the title. So, and I was just showing this and this plot now. So, do you see your faces? No.
We can see. We depending on how people have their screens configured, we can see our own faces. Yeah.
Okay, so basically what I'm showing here is an inflated brain surfaces, left hemisphere. This is the ventral part, so this is the anterior part, this is the posterior part, so this would be V1. And this is the ventral occipito-temporal cortex, right? And it has been known from a while ago that there is a region there that usually is being called visual orphan area that is more responsible to words than other categories of visual stimuli. And in our case, we call that the VOTRC or VOT reading circuitry. And now it's not moving. Okay. And just in case, I want to explain as well what a population receptive field is, which is the technique we use in our study. And the population receptive field would be of a voxel, and voxel in the visual cortex is the portion of the visual field in which the stimuli, so this would be a ring that is expanding, that the stimuli is evoking a response in these voxels. And the visual cortex, we know that is retinotopically organized. So we know that that the organization of the visual cortex have a direct topographical relation with the visual field. And these population receptive fields we can characterize with the location of the center, which can be Cartesian, like X and Y, or we can use angle and eccentricity to show where the center of the pRF is. And then we've got the size as well, because usually the more foveal voxels, the size of the population receptive fields are smaller. And when we go more to the periphery, the population receptive field size is usually bigger. So in 2017, I was talking about this other work, and they showed that the eccentricity, so the location of the centers, is stimulus dependent. So in this region, in the VOTRC. So, and it's a really big difference. So between 2 and 4 degrees, both ventrally and dorsally. This is area around an IPS IPS 0, 1 around this area, we see that the words are much more foveal, so that the center is usually located around less than 5 degrees, and the checkerboards and usually 6, 7 degrees. So it's a big difference, and this happens as well in the field of view. So basically, the field of view of a region of interest, and in this case, our region of interest would be the VOTRC, the visual orphan area. So it defines the portion of the visual field that evokes a response in any of the voxels in that array. So it's basically, we are aggregating the pRFs of all the voxels in our array, right? And we see how the field of view available for words, it's much more foveal than the one for checkerboard. So basically, this result and this result are the same, looking at the differently. And oops, sorry, I went back. Yeah. So to understand this stimulus dependence, we ran this new project. And we want to show the main result we have, and to be able to discuss with you. And what we did is we analyzed the areas that are likely the inputs to the VOTRC. So the signals here, so this is a little bit simplistic, but we assume that, and as the previous talk was saying, first from the eyes, we go to B1, B2, B3, HB4, BO1, and then only then it will arrive to the VOTRC. And for that we used 20 subjects, only English, that they were from the previous experiment, and a new set of subjects that they were watching both Hebrew and English. And we were using the moving bar paradigm as we see here. And inside the bars, we have our checkerboards or words, which is this case. And these are English words. We were placing Hebrew words as well. And as a control, we place false fonts as well. So we are usually the bars have been used typical retinotopy experiments, but here we use this evolution on the paradigm. And let's see if it moves. Yeah, and the main result we observed is the one on the title, that there is this gradient when we move from B1 all the way to VOTRC. We see that B1, B2, B3, we already start seeing a shift all the way to the VOTRC. So I'm going to explain a little bit what's on the plots here. So in the x-axis, we've got the eccentricity for words. Eccentricity, how far from the center is the center of the pRF. From the fovea is the center of the pRF. And the y-axis, we've got the eccentricity for the checkerboards. And if there wouldn't be this stimulus dependence, all of the points would be in top of the identity line. And we added this 5-degree bar in order to control for the noise. So these are noisy measurements, and if it's inside the bar, we would say, okay, it's basically the same. But we see how starting in B1, which is always imperceptible, this gradient, this stimulus dependence starts growing and being more significant. In HB4, it's basically clear that all the checkerboards have more eccentricity, and BO1 as well. And in the VOTRC, basically there are no word pRF centers that are wider or more than 5 degrees, and basically they disappear from. We see nothing here, and basically all the checkerboards are organized vertically, right? that's our main result and what I would like to discuss with you later on. So just to validate the method, we showed false fonts, which false fonts, you know, they look exactly the same as words. So visually, they are the same as words, and they have the same statistical regularities as words, but they don't carry any linguistic, no phonological, no meaning, no semantics, no any linguistic information. And we see that when we use false fonts, B1, B2, B3, B4, B01, all of them look very symmetric to us. In the case of VOTRC, we see that maybe there is some preference for the false fonts, or more eccentricity for the false fonts, but it's not statistically significant. And we did the same with the Hebrew and English words. So these are Hebrew speakers that they were watching these two different scripts, and basically the results fall in the identity line as well. So, well, first of all, we are trying to understand why this might be, why might be happening that this this shift is occurring, and why the population receptive field when we are watching a word is different to the checkerboard. And then another thing that we are working on is that basically this measurement is giving us the field of view available when we are watching words is different to the field of view available when we are watching checkerboards or other type of visual stimuli. And we think that this could be useful for characterizing the individual reading abilities. So that's one of the directions we are working. And yeah, I think this is basically it. So thank you for your attention.
All right, thank you very much, Gary. That was an excellent talk. Really a lot to think about. We have time for only a few quick questions. So if you've got a question, please post it in the Q&A. I'm gonna ask a question about, well, actually, I'll go first to the question from one of our panelists. Okay. Jasper asked about the reliability of the two different stimulus classes with the pRF reliability. So how does the R² value compare between words and checkerboards?
Okay. So that's a good question. And I had the slide prepared here. Not the slide, a drawing, because this is something we'll be working on. So can you see my screen now? Or are you seeing still the presentation?
We still see, thank you for your attention, but yes, we see your screen.
Okay. No, then I'm going to stop sharing, and now you just don't see anything, right?
We still see your screen. I'm gonna have to. So if you can answer really quickly, we have time for one more question. Otherwise, this might be
okay. Yeah, I wanted to show the plot, but now I'm stuck in Zoom wall. Okay, share screen. It's going to be very quick because he will see it. So now you see the thank you for your attention again, right?
Yeah, we see your screen.
Okay, so this is the R² and in the different places, and we see that the variance explained for when we are watching words or checkerboard, it's basically the same. Yeah. So I think one picture speaks more than 1,000 words, so that's why I wanted to show this.
That certainly that is a convincing plot.
Yeah.
Okay. So we have a question from Hans Optebeek. Could the bias towards foveal fields be related to spatial frequency distance differences in the relevant stimuli?
Yeah, that's a good question, and that's one of the follow-ups we are doing. And one of the things we are watching is that this difference of eccentricity, as we are watching exactly the same voxel, and it's radial. So it's not that we've got 2 degrees in this direction for words, and then we got 5 in the other direction. It's the same voxel. It organizes in the same, and now we are trying to test all of these tests he's saying. So controlling for the width of the bars, size of the stimuli inside of the width of the bar, in order to be able to, so for example, we didn't put it here, but we see a difference when we are using small words or big words. So I don't know if this is answering his question.
Okay, I think that'll do. I'm gonna ask you a yes or no, a one-word answer question. So you've shown us data that suggests that you're getting different PRF values for the stimuli of choice. Does that mean that we need to map for any visual area? Should we only be considering its preferred stimulus, or do you think that there's transferable information?
I don't know. We are worried about the VOTRC.
Do you think words are a special case?
And I don't know. That's what and why should be different, right? Because all of these areas have been connected hierarchically, and why some it's giving us a different. We don't know. That's the question. So it's a good question.
Yeah. All right, great.
Thank
So we need to move swiftly along, but I want to thank you again. That was a great talk. Really interesting data. So our last talk of this session.